In our 25th lecture in real analysis, we are going to discuss a few weird functions, and so functions with some strange and unusual properties. And then we're also going to talk about the formula for the derivative of a function's inverse and the inverse function theorem. So to discuss our first weird function, let's recall from a previous lecture that we proved that if a function is differentiable, then the function is continuous. So you can't be differentiable without being continuous as well. We also saw that continuity does not imply differentiability. So differentiability is stronger than continuity. And the classic example, typical example of this is just the absolute value function. And so you can take a function with a corner like this. So in this example, and of course, so we could have this extend out further, right? So in this example, we have a function which is differentiable at every point except here at the origin. So it's a continuous function everywhere, and it's differentiable almost everywhere. So it's differentiable except at that single point there. So that shouldn't give you the impression that, that shouldn't necessarily give you the impression that a function is, if you have a continuous function, that it's going to be, differentiable at only a few, it's only not going to be differentiable at a few isolated points necessarily, or relatively few points, maybe I should say, because, you can do something like this. So we can extend this to have this kind of sawtooth function. And for definiteness, let's just say, we could say this is 1, 2, 3, 4, -1, -2, -3, etc. So we see that, we actually have an infinite number of points where this function here is not going to be differentiable. Okay, so analogously to why this the absolute value function is not differentiable at the origin, this function is not going to be differentiable at every one of these corner points here. But in a sense, even though there's infinitely many places where this is not differentiable, in a sense, this function is differentiable sort of most everywhere on the real line, right? There's only these isolated number of points at which we have the problem that it's not differentiable. And you might think in some sense that this might be sort of the generic case, that if you have a continuous function, then it's got to be mostly differentiable, right? In some sense, if it's continuous means sort of nice, continuous means you can kind of draw the graph, roughly speaking, your high school intuition. Continuous, even though we have a fancy mathematical definition for it now, you sort of still think of it as something you can continuously, nicely draw the graph of, and maybe there's some corners where it's not going to be differentiable, but it should be sort of mostly smooth and differentiable. However, this turns out to not be the case. So there's sort of general fact here. Or maybe I'll phrase it this way. I'll say caution. So one should not think of a generic continuous function as being mostly differentiable. And the fact is, that there are continuous functions which are differentiable nowhere. There are continuous functions which are differentiable nowhere. And in fact, as an example, I can sort of explicitly write down an example. If we take that function h up there, so we can take that h and we can define f of x. Well, the basic idea is you're going to take this h function here and you're going to add more spikes to it. So you're going to make the spikes, so you're going to put spikes on these straight parts, right? So you can sort of think about this as you've taken the 0 function and then you've put some spikes on it. And now you're going to take these flat parts of this and you're going to put smaller spikes on there. And then for each of the flat parts of those, you're going to put smaller spikes on those, and you're just going to keep repeating that process. So we can make the spikes more frequent by doing a scaling inside on the x, and we can make them smaller by just dividing. So what you can do here is you can take your h function there, you do 1 over 2 to the n h of 2 to the n x, and we're going to add on those spikes by actually just adding. So we're going to add these functions up like this. So for each fixed x, you have a bunch of numbers, right? You have these h of 2 to the n x. You figure out what all of those are and divide by 2 to the n, and then you add up that series. And whatever the numerical value is, that's your value for f of x. Okay, and so for doing this for each x, this defines a function. You have to actually check that this gives you a well-defined answer. The 1 over 2 to the n helps make this series converge here. And then there's a bunch of work to do to show that this is actually a continuous function and that it is differentiable nowhere. And we're not going to do that work, but just sort of satisfy ourselves with the image that this is plausible. Basically, you're making a function which is kind of spiky, infinitely spiky at arbitrarily small scales by doing this sort of collapsing. So this, for this 2 to the n, whenever you do this, you're scrunching this h function down by a factor of 2 to the n. So it's making all of those, it's jamming more and more of those spikes into a very small portion of the graph, and then you're making them small by dividing by that by multiplying by that 1 over 2 to the n. Okay, so we're not going to do the work for that, but that indeed is an explicit example of a continuous function which is nowhere differentiable. And here's another fact. So maybe I can call this fact 1. So fact 2. Fact 2 is that most continuous functions are like this. Most continuous functions are differentiable nowhere. So there's a way to make the statement that the functions which have a derivative at even one point are very small in the space of all continuous functions. So there is a way to make precise the statement that the set of continuous functions which have a derivative at least one point sorry for the double ats, at least one point is very small in the set of all continuous functions. I'm not even really going to try to indicate the sense in which you can make that precise, but you can. Okay, so in some sense, the generic continuous function never has a derivative, has a derivative at no point. If you sort of grab a random continuous function, then it's not going to be ever differentiable anywhere. And so in a way, the continuous functions we're used to thinking of, which are differentiable at most points, are very atypical. Okay, so most of your continuous functions are, in a way, they're quite badly behaved, and they have behavior that most of us would consider kind of aberrant. But nevertheless, that's the case. So mathematics is often surprising in this way. Moving on to our second weird example, I want to recall a fact from, I think, the previous lecture. As a consequence of the mean value theorem, we showed that if a function has a derivative which is equal to 0 everywhere in an interval, then the function must be constant on that interval. Okay, so by the mean value theorem, you look at f of x minus f of y over x minus y, and that has to be equal to the derivative at some point in between. And if that is always equal to 0, then that says f of x always equals f of y. The numerator is 0. Okay, so this is a very sort of familiar fact. It's intuitive, right? The derivative equals 0 means the function's never changing. The rate of change is always equal to 0, so it must just be remaining constant. But there's a sense in which this theorem is almost false. And to see this, we're going to look at an example called the Cantor function. As above, this is really just kind of going to be a sketch of the idea here. I'm going to skip over some details to just give us some time to relax and just think about some interesting example and not worry ourselves with the details too much. So the function here, it's defined on the interval from 0 to 1. Sorry, this line really isn't very straight, is it? Let me try this again. A little better. Okay, so the function is like this. It's equal to 0 at 0. It's equal to 1 at 1. And then the rest of the function is filled out according to the Cantor set construction. So when in the Cantor set we take out this middle third, so the middle third here from 1/3 to 2/3, and let's see, let me try to make that better, 1/3 to 2/3, the value of the function in that interval is going to be the average of these two values. So it's just going to be 1/2. Okay, so the value of the function is 1/2 there. And, okay, so that's 1/2. And then in the middle third, so here we have our first third, we have the middle third of that's going to be removed when we're constructing the Cantor set, and the value of the function will be halfway, will be the average between this and this. So that's going to be 1/4. And the average in this middle third over here is going to be the average of 1/2 and 1. Okay, so that's 3/4. And we keep going along like this. So take out a middle third here, and that will be like that and like that. Take out a middle third here and here, and we'll get something like that. And then the middle third's in between that, so I'll just sort of try to indicate this like there, 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 and there, there, and there. And that sort of keeps going along. You start to get this staircase kind of picture. And I don't know if this has a standard notation, but we'll just, I don't know, we can call this C of x. And so some facts here. Okay, so this, as I've kind of defined it here, is defined on the complement of the Cantor set because it's defined it for all the stuff that you're removing from the interval, the closed interval from 0 to 1 to get to the Cantor set. So the first fact is that this can be defined, as a continuous function on 0 to 1. So this really can be, extended from the complement of the Cantor set to the entire interval from 0 to 1. Not really surprising. I mean, basically what you can do is sort of extended by taking limits. So that the Cantor set is going to be, a limits of things in the complement of the Cantor set. So you can extend this definition to all of 0, 1. So C of x can be, so first fact, C of x can be extended to a continuous function on the closed interval 0, 1. Okay, so that's sort of the main thing. This really does define a function. It's an increasing function. So it's increasing. It's increasing despite the fact that f prime, we're calling a C prime. Despite the fact that C prime is equal to 0 almost everywhere. So clearly, by the way we've constructed this, being constant on these open intervals, on any one of these open intervals, the derivative is just 0. So this function has zero derivative on the complement of the Cantor set, which is this big open set, which sort of intuitively has length equal to 0, 1. So remember, the Cantor set has length equal to 0, whatever the notion of length for a set as weird as the Cantor set. The technical term is measure. So this is really properly an object in measure theory. But we'll just stick to the intuitive kind of idea of length. So the almost everywhere here is on the complement of the Cantor set. So 0, 1 minus the Cantor set. And so this function is very nearly a counterexample to this fact here. So this function is not constant, manifestly not a constant function, and its derivative is 0 nearly everywhere in the open interval from 0 to 1. So hopefully this gives you increased appreciation for your intuition and for the mean value theorem, for being able to validate our intuition when we are really kind of on a knife's edge here. So once you start opening your mind up to some of the weird counterexamples that you can find in analysis, like the continuous but nowhere differentiable function we saw in the previous item, you start to doubt your intuition. Like maybe your intuition about this statement being true should be doubted. So it's kind of a minor miracle that the mean value theorem is able to validate our intuition when our intuition is so often lacking, and it's just a matter of a lack of imagination that our intuition can lead us astray. So in this case, it doesn't, but it is a fragile, delicate matter. Okay, so that's the Cantor function, a increasing function, which has derivative 0 almost everywhere. For our third example of kind of weird function in analysis, let's recall the intermediate value theorem, which says that a continuous function has to have the intermediate value property. And the intermediate value property of a function on an interval is just the following. If you have any two values of your function, g of c and g of d, and an alpha between them, and so g of c could be less than g of d, could be bigger than g of d, we just need an alpha in between the two, then g takes on this value alpha for some t between c and d. Okay, so this just means that, so this just intuitively means you take any two values of your function, then anything in the middle has to be hit somewhere in between those two values in the domain. Okay, so that's a familiar property of continuous functions that we know from the intermediate value theorem. And we saw in the last lecture that Darboix's theorem says that any derivative, so any function which is the derivative of some other function, also has the intermediate value property. And this is interesting because remember we saw that there was a function which had a derivative which is not continuous. So this gives us an example of a function that has the intermediate value property but is not a continuous function. Okay, so this tells us that that continuous functions and functions with the intermediate value property are not exactly the same thing. So let's recall that example. So however, the functions, so we had f of x was x squared sine of 1 over x. The derivative of this function is not continuous at x equals 0. So it has a derivative everywhere, but the derivative is not continuous at x equals 0. Has a derivative which is not continuous at x equals 0. And so what that tells us is the derivative of this function has the intermediate value property, but it's not a continuous function. So thus, being continuous, or I guess I can say it this way, so thus the intermediate value property does not imply continuity. So we have continuity implies the intermediate value property by the intermediate value theorem. This does not imply continuity. However, in a sense, this function is not a very strong counterexample to this fact because it only fails to be continuous at a single point. It's much like the fact that it's much like the absolute value function in our discussion of whether continuity implies differentiability. So of course, the absolute value function gives a counterexample to the assertion that continuity implies differentiability, and because it's just not differentiable at a single point. And but much like in that discussion, where we found out that continuity doesn't have to mean differentiable basically anywhere, we're going to find here that just because you have the intermediate value property doesn't mean that you have continuity sort of most anywhere. Like, so this example, the derivative of this function, you might think, well, it has the intermediate value property. It only fails to be continuous at a single point. So maybe the intermediate value property is kind of mostly correlated with continuity. So maybe the intermediate value property implies some kind of continuity. In fact, that's not the case. So it turns out, so here's again a fact. So the fact is that there are functions which satisfy the intermediate value property, but which are discontinuous at every point. Okay, so even though the intermediate value property is a consequence of continuity, there's really some sense in which, looking at the converse, the intermediate value property really doesn't have a whole lot to do with continuity, in the sense that if you're just talking about functions with the intermediate value property, they might be completely unlike any kind of continuous function. And the examples that I have in mind here, they're actually quite unusual. They take every real value in any interval, no matter how small. So in fact, there are functions which attain every real value in any interval. Okay, so no matter how small an interval you specify, this function will take on, the range of the function restricted to that interval will be all of the real numbers. So they're quite strange. And so just this fact, so if you can construct a function which has this property, they obviously satisfy the intermediate value property, right? So if you take, call this function g, if you take g of c and g of d, so you have some interval cd, and so you have c and d. You look at the value of your function at these 2 points. Well, in the interval between them, this function will take on every real value. So it'll of course take on any value between g of c and g of d. It's in fact much stronger than that. It's taking on every real value, not just all of the values between g of c and g of d. And also, if you have a function which does this, takes every real value in any interval, it can't be continuous at any point. It's automatically discontinuous at every point, because a continuous function, if a function is continuous, then it has to be locally bounded. So if you have a function, any function which is continuous, if your function is continuous at this point c, if you look at the image point f of c, right, the fact that it's continuous means that if I put a little epsilon ball around this f of c here, I have to be able to find a little neighborhood around c where the function, which the function drops into this other interval here. Right? So in other words, the image of this interval by the function has to be bounded inside this interval. But a function which takes on every real value in any interval, right, can't possibly have this property. So if we had such a function, if f is such a function up here, then f is going to take on every real value in this small interval of size delta around c. So it can't possibly fit in this epsilon neighborhood around f of c. Okay, so the claim basically is that you can create a function which attains every real value in any interval. And since I don't want to make this a complete black box, just sort of something that seems like it's incredibly difficult to do, because actually it's relatively straightforward to do once you have the idea. The idea is not really easy at all to think up, but in a way it is kind of natural, depending on how much math you've seen. So the whole construction, once you have the idea, really only takes like a page of work. So the basic idea, the outline of the construction. So the first point is you consider translates of the rationals. So for example, consider something like square root of 2 plus the rational numbers. So this would be the set of all real numbers. So this is the set of all real numbers R, such that R equals the square root of 2 plus Q, where little q is in the rationals, is a rational number. Okay, so you just shift all of the rational numbers over by square root of 2. And then you could do this, also with square root of 3 plus the rationals. And in general, for any real number, and so for any real number R, you have R plus the rationals. And so these various translates of the rationals are going to fill up all of the reals. So these translates, so each of these translates is a set, and the union of these translates is R. Okay, so in fact, all the distinct translates here forms a partition of R. So these two things, two different translates, they're either identical or they have no overlap. They're completely disjoint. Okay, so you sort of have these non-overlapping, weird-looking subsets. I mean, they're weird in the sense they're these kind of sprinklings of points, right? So they look just like Q, except they're just moved around. And then what you note, there are uncountably many such translates. There are uncountably many such translates. And the reason for that is quite simple. Each of these translates is countable themselves. And so if there are only countably many of them, then the reals, because the union of all of them is the reals, then the reals would be countable if there was only countably many. You'd have a countable union of countable sets. Okay, so once you do that, then you choose a function from this set of translates to the reals. So you choose a surjective function from the set of translates to the reals. So call the set of translates, the standard notation for it is R mod Q. So what you can do is choose a surjective function. Because it's uncountable, the reals are uncountable. You can show that they have the same cardinality. So you choose a surjective function. I don't know, say G from R mod Q to R. And then the fourth step is your function f is going to be this composition. So you're going to have a function like this. So this is going to be your function g here, your surjective function that you chose, and this is a natural function. So this function, you can call it p, is a natural projection from the real. So you take any real number and you just send it to the translate R plus Q. And then this will go to G of R plus Q. And this defines your f. So f is going to be G composed with P. So the claim now is just that this is your function. So this function takes every real value. Okay, so this is the function you wanted to construct. So f is the function we want. And why is it the function we want? Well, basically, it's because any one of these translates. So any translate R plus Q is dense in R. That is, its closure is all of the real numbers, just like the rationals. So if we have some interval, no matter how small, there's going to be points of this R plus Q in there. Okay, so this R plus Q will be, we'll find points of it in there. And so since every translate, we can find elements of any given translate in our interval, no matter how small, since this function g is surjective onto all of the reals, then every real value is going to be represented in this interval. Okay, so that's the construction. So once you have this kind of function which can take every real value in any interval, then you have a function which has the intermediate value property, but which is discontinuous everywhere. Okay, so continuity implies the intermediate value property, but the intermediate value property very much does not imply continuity, not even close. However, here's a general theorem that tells us a condition that we can add to the IVP, the intermediate value property, which makes a function continuous. So if we have a function from an interval to R, which has the intermediate value property and is monotone, that is, it's either increasing or it's decreasing, then the function is continuous. Okay, so there is a general situation in which we can say that the intermediate value property implies continuity. So we get a converse to the intermediate value theorem as long as we also assume that the function is monotone. So let's take a look at this, how to prove this theorem. Okay, so we'll assume f is increasing for definiteness. The decreasing case follows from this one by considering negative f. From this one by considering negative f. So if you have a function which is decreasing, then negative f will be increasing. You can apply this proposition to negative f, and then you find negative f is continuous, and therefore f is continuous. Okay, so we can just assume f is increasing. So we have to prove continuity, so we'll let c be an element of our interval here. And by the way, I guess I should just say that this function or this proposition works for any kind of interval. We're just doing open interval, just again kind of for concreteness, but the proof can easily be minorly, changed in minor places to extend to any interval. Okay, so we'll let c be an element of our interval here, and epsilon greater than 0 be given because we have to prove continuity. Okay, so we still somehow have to find a delta to respond to this epsilon. and it might not really be clear where we're supposed to get that delta from. So let's draw ourselves a picture. Okay, so we have A, B, and C, and let's say we have f of c. Okay, so we have f of c here, and our function is increasing. So our function could be doing something like, I don't know, it's doing something like this. Okay, so our function is increasing. So this value here is f of c. And then we have our epsilon given. So our epsilon and so we have f of c plus epsilon, f of c minus epsilon. We have this epsilon ball around here. And we have to identify a delta around c that lands us in this epsilon ball. Okay, so you can kind of go across. We're trying to identify a sort of how close do we have to come to c here in order to fall in this epsilon range here. And we can see this from our picture that here, right, we have this point right here, and we have kind of this point right here. So we can't go further out than this, right? So so if we look at this distance over here and this distance here, whatever the smaller of those two would be, that would be our delta. We'd want to stay within that amount of c so that we didn't go out of these bounds. And the reason this is going to work is because, so the reason this delta works is because we know our function is increasing, right? We know that our function, so the value that our function takes here, it's, everything before that is going to be less. So this is sort of f of c plus epsilon. That's the value our function is taking here. And anything before that is going to be less than that, right? Because our function is increasing. So we're going to be within the epsilon of f of c here. Okay, so we're going to be less than that. And below here, so we have f of c minus epsilon, our function sort of taking that value here. Anything to the right, we know it's going to be above that. So we're using the fact that our function is increasing here. So once we sort of find these, if we can find these points here where our function is taking on these, the extremity values, f of c plus epsilon, f of c minus epsilon, then if we stay inside of that, we should be good to go. But actually, I'm kind of telling a slight simplification here. Really, we could kind of be in trouble. So if we look at this so if this is f of c minus epsilon, if we look at a point where our function takes on that value, it could be, our function being increasing doesn't mean it's strictly increasing. So our function could actually be flat. So we could take on the value f of c minus epsilon here, and then to the right, we could still be taking on that f of c minus epsilon value. And we wouldn't be strictly within a distance of epsilon from f of c. We'd sort of be on the boundary there. So really what we're going to do is this value here, this is going to be f of c plus epsilon over 2. So just to keep that strictly within those that epsilon distance around f of c. So this here, this will be f of c minus epsilon over 2. So f of c minus epsilon over 2. Okay, so if we can sort of find find values where a function takes on f of c minus epsilon over 2 and f of c plus epsilon over 2, and then we just stay to the right and left, sort of respectively of those around c, then that will sort of tell us what our delta is. That's the basic idea. Is you kind of just look at this picture and use the increasing. Okay, so we're going to try to turn that into an actual valid proof. The only other complication I guess I should mention is that it could be that your epsilon's kind of big. Somebody could give you a big epsilon, and then this f of c minus epsilon over 2, that might actually extend quite far down, and it might extend so far down that your function doesn't even go down that far. And in that case, you're not going to be able to find a value that reaches that, but that's not a problem. If all of the x between a and c, if the value of the function at those x is always above f of c minus epsilon over 2, then that's clearly not a problem, right? So that's actually a favorable case. We'll just sort of have to take care of it separately. So let's consider f of c minus epsilon over 2. So there are two cases. So the first suppose that f of c minus epsilon over 2 is less than f of x for all x in the interval from a to c. So in this case, we're going to let delta 1 just be the distance from a to c. Okay, so this is just telling us we can go to the left as far as, we can go to the left of c as far as a and still not go that far from f of c. So in this case, we set delta 1 equal to c minus a. So then if x is in the interval c minus delta 1 to c, and c minus delta 1 is just a, we have, well, just this inequality here tells us that f of c, so f of c minus f of x, so f of c minus f of x, first of all, since our function is increasing, this is bigger than or equal to 0. And from this inequality, f of c minus f of x is less than epsilon over 2. Which is less than epsilon. Where the first inequality is because f is increasing. The second case, okay, so we sort of identified a left delta. So basically the plan is we're going to identify how far to the left can we go, how far to the right can we go, and then take the minimum of those. So the second case is that this is not the case for all x. So in other words, some f of x is less than or equal to this. The second case is f of x is less than or equal to f of c minus epsilon over 2. So that's this picture here, right? So you have f of c minus epsilon over 2. You have some x which are less than that. For some x in a, yeah, I guess it's going to be in the open interval from a to c because, f of c can't be less than or equal to f of c minus epsilon over 2. Okay, so then the point is that by this inequality and the fact that this is less than f of c, we can use the intermediate value property to say there has to be some x where this value is actually hit. So since f of x is less than or equal to f of c minus epsilon over 2, which is less than f of c, by the intermediate value property, gives an x1 in a C such that f of x1 equals f of c minus epsilon over 2. So then the point is, well, to the right of that x1, the value of the function has to be bigger than or equal to this by the increasing property. So since f is increasing, f of c minus epsilon over 2, that's less than or equal to f of x for all x in the interval from x1 to c. And so just like in the first case, so in this case, set delta 1 to be the distance from c to x1. So that'll be so this x1, we don't want to go any further left than this. C minus x1. Then if x is in c minus delta 1, c minus delta 1 is just x1, comma c, we have we have f of c minus f of x is less than or equal to epsilon over 2, and by the increasing property, it's also greater than or equal to 0. So we have 0 less than or equal to f of c minus f of x less than or equal to epsilon over 2, which is less than epsilon. So then a completely analogous argument, gives a delta 2 such that maybe I should back up. Completely analogous argument with f of c plus epsilon over 2 gives a delta 2. And I should say, this delta 1 up here, this is greater than 0. Right? My x1 was in this interval, open interval from a to c. So this is going to give a delta 2 greater than 0. That's important. All right, we have to respond with a delta which is greater than 0. A completely analogous argument gives a delta 2 such that x being in, now it's in the interval, we're going to the right. So we have c to c plus delta 2, such that that implies that 0 is less than or equal to, this time it's f of x minus f of c. Right, our function, now we're moving to the right, so our f of x value can only increase, and that is less than epsilon. So thus, it immediately follows that if x if the distance between x and c is less than delta, where delta equals the minimum of the two deltas, the delta 1 and the delta 2, then the absolute value of f of x minus f of c is less than epsilon. Okay, so x is either to the right of c, in which case x is in this interval here, right? So delta can only be smaller than this, delta 2, so x would fall in this interval here, and then f of x minus f of c would be, and so the absolute value of f of x minus f of c would be f of x minus f of c because it's greater than or equal to 0 and it's less than epsilon. And then you'd have a similar argument with the if x was to the left of c. Okay, so that completes the proof. So that shows us how to pick our delta, and we get continuity. Okay, so intermediate value property does not imply continuity, very much does not imply continuity, but if you add monotonicity, then it does imply continuity. All right, so now I want to talk about the derivative of an inverse. This might be familiar from calculus. So you might remember trying to take the derivative of a function like the arctangent, the inverse of tangent. So how do we find the derivative of arctangent? Well, we do a trick like this. Since the arctangent is the inverse of tangent, we apply tangent to both sides here. We have tangent y equals x. And then we take the derivative with respect to x. So this gives us secant squared of y, then times the derivative of y with respect to x, because y is this function of x here, so we have to use the chain rule. And that equals 1. And so that tells us that dy dx is equal to 1 over secant squared of y. And y, remember, so we want this as a function of x, is just arctangent of x. So this is 1 over secant squared of arctangent of x. And if this doesn't look familiar, that's just, remember the last step is that secant squared is 1 plus tan squared. So then you have the tangent of arctangent is just x. So we get 1 over 1 plus x squared. So this simplifies to 1 over 1 plus x squared. But this is the formula really that I wanted to look at, because that's the one that generalizes. So let's take this idea in general and say we have an inverse function. So we have some function f and we're looking at its inverse, right? And we want the derivative of this inverse function. So the basic idea here was that we used was to compose this inverse with the function itself, and then that's going to be x, just because that's the definition of it being the inverse. So if we take this inverse and we compose with the original function, that just gives us x. So then again, we take the derivative, and by the chain rule, we get the derivative of the function f at the inverse, right, composed of the inverse, then times the derivative of the inverse, and that equals 1. And so then we can solve, as we did here, solve for the derivative of the inverse. That's just going to be 1 over the derivative of our original function, which up here was secant squared, and then composed with f inverse of x. F inverse of x is just our y. And so up here our y was our inverse function. Okay, so this is all lining up nicely. So this implies that f inverse prime of x is, to be short about it, it's just the inverse of the derivative of the original function. So the derivative of the inverse is the inverse of the derivative. And it's 1 over the derivative. But this derivative, it's not at x, x is in the domain of the inverse function. So if you want to be talking about the derivative of the original function, you have to go back to the original domain. So you have to actually do f inverse of x. Okay, so it's 1 over the derivative of the original function, but then evaluated back in the domain of the original function, use the inverse function to go back. And that lines up with this here. F prime up here was secant squared, and then the f inverse of x, that was the arctangent of x. So that is the formula. So that's all relatively simple. You can teach this to a relatively bright calculus student. So why am I showing it to you? Well, there's actually a problem in our calculation here. The problem is that, so let me stop us here. So we have a problem. And the problem is that we actually assumed that the derivative of the inverse existed. So we assumed that f inverse prime exists. So basically we showed that if f inverse prime exists, then this formula has to hold. So what we showed is something like, so what we showed is that if f inverse prime exists, then it has to satisfy a particular formula. Then it has to a particular formula. Okay, but we didn't actually justify that the derivative exists. I mean, it's conceivable that the derivative may not exist. So for example, if you take f of x equals x cubed, then f inverse is x to the 1/3. Right, so this has this is a perfectly, this is a differentiable function, continuous and differentiable, and it has an inverse, right? That's defined everywhere. It's a continuous function defined everywhere, but the inverse does not have a derivative at 0. So f inverse prime at 0 does not exist. This is an easy calculation. You can do it directly from the definition. It's easy to see that that derivative does not exist. And the problem is because this formula, right? So if you take, so according, if you tried to use this formula, so let's take a look at it. So if you look at 1 over f prime of f inverse of x, or f inverse of 0. So the derivative is 3x squared, right? So something squared, and then the inverse at 0 is 0, so you're going to get 0 squared. So this is times 0 squared, and we have a whoopsie daisy, because this is a 0 in the denominator, right, which is not well defined. Okay, so the fact that this derivative doesn't exist, which you can check just by using the definition, sort of lines up with the fact that this formula breaks down because you're dividing by 0. Okay, so that's one issue. But basically, if you banish that issue, so if you assume that your derivative is not equal to 0, then it will be the case that that your inverse is differentiable and you have an inverse, and this formula holds. So that's the theorem we'd like to justify. So let me just say here, the issue here is that f prime equals 0 at x equals 0. Okay, so our next theorem, we'll see that specifying that the derivative is not equal to 0 is part of the hypothesis. All right, so here's the statement of the theorem. So suppose we have an injective function on some interval, so that we have an inverse function. So we have an inverse defined on the image of that interval by f. So the inverse function takes that image back to AB. Okay, so we have an inverse, and let's also suppose that our function is differentiable and not equal to 0 on this interval. Okay, so our original function is differentiable, derivative not equal to 0, so we can make this formula work here. Then, in fact, f inverse is differentiable on the image, and the derivative satisfies the formula that we talked about before. The derivative of the inverse is, in a sense, just the inverse of the derivative, multiplicative inverse of the derivative. Okay, so let's try to look at the proof. I don't think we're going to completely finish the proof. The proof might bleed into the next lecture, but I want to at least set things up so that we're at a good spot with the proof before we end. So to begin the proof, let's compute. So we're going to compute f inverse prime. And I'm going to compute this at I'm going to call it y naught. And the reason is that my f, I'm going to think about the variables in this domain as being labeled by x, and then over in the image, which is the domain of f inverse, those are going to be labeled by y. All right, so I think this is psychologically just useful to use this. Okay, so we're sort of over in the domain of f inverse here. So f inverse prime of y. What is this? This is the limit as y approaches y naught of f inverse of y minus f inverse of y naught over y minus y naught. And then the main trick here to get this, so we know what the formula should be, right, from the chain rule. It's this 1 over thing. So we should have some sort of inverse thing happening. This should sort of be an upside down difference quotient, right? This would be the difference quotient for f prime upside down. And you can kind of see that in the following way. So if you think about this y as, right, this is over here in the image of f. So you can think about y as f of x, and this as f of x sum x naught. And then y here, this is f of x, and this is f of x naught. And so what you would get here is, if you compose the f inverse and the f, that's just going to get you x, right? So you're going to have x, and then similarly x naught there, and then over f of x minus f of x naught. And then, right, you have a limit in here. Right, so you do see kind of upside down difference quotient here. Okay, so I don't want to change variables. I have this limit with y. I don't want to change over to x's. That's, I don't know. I just don't want to do that. So I'm going to set this up a bit of a different way. Okay, so I just need to get rid of that. So what I can do instead to keep the y's is, right, like I had in that difference quotient, I want to see f's down here, right? I want to see the inverse of a difference quotient for f prime, so I want to see f's in the denominator. So what I can do is I can do f of f inverse, right? So that y, I can write that as, so you have the limit as y goes to y naught. This is f inverse of y minus f inverse of y naught over f of f inverse of y minus f of f inverse of y naught. And so this is just the limit as y goes to y naught of f inverse of y. And now I'm flipping things over, and I'm going to put a big inverse on the outside over f inverse of y minus f inverse of y naught. And I could put a big inverse around this fraction, but then the limit, right, the inverse, inverting is a continuous function, so I can, or well, just the, the algebraic limit theorem, right, 1 over, the limit of 1 over something is 1 over the limit. And what this is, I want to think about this as a composition of functions. So I have the f inverse of y. So y naught is just fixed. I have this kind of variable y. I want to think of this f inverse of y here. That's the inside function of my composition. And then this big fraction is the outside function. So this is going to be the limit as y goes to y naught of h of f inverse of y. Okay, inverse here, where h of x is f of x minus f of f inverse of y naught over x minus f inverse of y naught. Okay, so this is going to be, it's going to be that when x is not equal to f inverse of y naught, and it's going to be equal to the derivative, so this is going to be the derivative of f at f inverse of y naught when x equals f inverse of y naught. All right, so this isn't defined, this expression isn't defined when x equals f inverse of y naught because of the division by 0, but with this being the definition at f inverse of y naught, this function becomes continuous, right? So this is the value of the limit. We know that our function f is differentiable, so the limit of this expression as x approaches f inverse of y naught exists and equals that derivative. So note that h is continuous since f is differentiable. So then, if f inverse is continuous, we have, so let's continue our computation here. So we were computing f inverse prime of y naught. So f inverse prime of y naught. We got down to the point where it was the inverse of this limit, h of f inverse of y. And if f inverse is continuous, then we have this composition of continuous functions. So this limit, right, so that composition is going to be continuous. That limit is just h of f inverse of y naught. We'll have the inverse of that whole thing. And f inverse, h of f inverse of y naught is just f prime at f inverse y naught. So this will just be f prime of f inverse of y naught. And then that whole thing inverse, which is 1 over f prime of f inverse at y naught. Okay, but we still have this outstanding if here. So what we need to do, so we need to justify So first thing, definitely we need to justify that f inverse is continuous. It's not that surprising. We know that differentiability implies continuity, so it's not that surprising that we might need to know that f inverse is continuous in the first place in order to prove that f inverse is differentiable. And another kind of subtle point that I glossed over when we began this computation is we've been defining derivatives for points that are in the interior of an interval. Right, so we needed sort of a two-sided limit. We need to be able to approach this point from the right and from the left. But that's not exactly obvious for a point in the image here. Right, so the domain of f inverse is the image by f of this open interval AB. And it's not exactly obvious that interval should be open. Right, it could be that this interval AB, it might get folded over to a closed interval in some sense, right? So it could be the case that your f looks like that, and then maybe y naught would be this right endpoint D here. So we really kind of need to justify that y naught is actually an interior point. So we kind of need to prove that y naught is an interior point of the image f of AB. Basically, we're just, y naught is just an arbitrary point, so we're just need to say that every point of this image is an interior point. So essentially, we just need to say that this image is open. So let me just say it that way, that f of AB is open. And parenthetically, I'll remark so that y naught is an interior point. And this will be accomplished by the following things. So this is accomplished by the following. First, A will show that an injective continuous function is strictly monotone and on an interval is strictly monotone. That is, it's either strictly increasing or strictly decreasing. So in particular, this is going to show that the image here is open. So A will just by itself take care of 2. And then to take care of 1, to show that f inverse is continuous, we're going to use the proposition we proved before, which is that earlier in this lecture, which is that the intermediate value property plus monotonicity implies continuity. So we're going to show that the inverse function here has monotonicity and the inverse value property. So the monotonicity of f from A will easily imply the monotonicity of f inverse, and then we'll also easily be able to establish the intermediate value property. That will be straightforward. So we just need to show that f inverse is monotone and has the IVP. Okay, so if we can do these two things follow. That legitimates the computation we did above and would complete the proof. I'm out of time for this lecture, so I'll do that in the next lecture, and then we'll also look at the proof of L'Hopital's rule. So see you in the next video.